Okay, and we're away. So we're starting off with some folded beds. I'm just drawing a sort of random antiform shape there. And what we're going to be doing is looking at two different types of beds. So on these beds, we're going to have a sandstone in there, and we are going to have a shale in there. Now, key properties when we're talking about structural geology of sandstones and shales are they're competent. And by competence, we're talking about whether they are brittle or not. So sandstone, as we've discussed before, is what we call a competent rock. That means it's brittle. The shale is incompetent, which means it behaves in a more ductile manner. If we're talking about competent, we need to think about it being brittle. And the key thing that happens with brittle rock is that they fracture. When we're talking about incompetent, we're talking about them being ductile. And the key thing is that they sort of deform. And quite often that results in folding. Okay, so there are two types of rocks. What we've got here is we've got compression in, let's call it an east to west direction, is generally when you're looking at diagram, the looking north, that's the way they usually orientate them on maps to make maps and exam questions to make it easier for you to understand. So we've got our compression, got this fold being formed, this anticlinal fold. We'll draw in the axial plane there. Got to fold, always got to have an axial plane. And now we'll start focusing on the structures that are formed by these competent and incompetent rocks. So we'll start with shale, and shale contains, and it's often drawn like this, shale contains platy minerals and clay minerals. Those platy or clay minerals are sort of elongate in shape. And what you've seen before, hopefully, with that same thing you did with spaghetti, when you compress them, they line up perpendicular to the direction of compression. So we've got compression lining up perpendicular at 90 degrees. So what happens is, at the sort of main point of compression here, we get our platy minerals align at 90 degrees perpendicular to principal stress. Principal stress is the sort of main stress direction. So we've got our platy minerals lining up, and that is what we know as slaty cleavage. Of course, slaty cleavage, we start with a shale. When we've got compression, we often have metamorphism starting, and shale does turn to slate. And more often than not, in slate, you find slaty cleavage. Okay, so that's our alignment of minerals. Now, in our sandstone, generally rounded grains, you compress those, they can't line up. There's no way that they can line up. So we don't get slaty cleavage in sandstone because there are no platy minerals. And the other key factor to why we don't get slaty cleavage in sandstone is that it is a competent rock. Brittle, it fractures. So what we actually get in sandstone is on the outer edge of the fold, get tension joints. Now we get joints in, hopefully you can see that, we get joints in sandstones, brittle rocks, because when it's put under that stress, it fractures. Think about that outside edge of sandstone bed. It's actually extending. If you think of that book as the bed and it folds like that, that outer edge is actually being stretched. And that's why you get these tension joints forming on the outer edge of a folded sandstone bed. Okay, the other thing that we can get in this sort of area here is we get some recrystallization of platy minerals. Again, linked to that process of metamorphism. Okay, I'll stop the recording there.